Question 12 from the 2019 Advanced Higher Physics exam from the SQA. A student is performing an experiment to determine the speed of sound in air. The student uses the apparatus shown in figure 12a. The microphone is in a fixed position and the signal generator is switched on. A stationary wave is formed within the tube. And for 1 mark, we're asked to explain how a stationary wave is formed. Well, quite simply, a stationary wave is formed for this reason. The transmitted travelling wave from the loudspeaker is reflected off the closed end of the tube, and this reflected wave travels to the left and interferes with the transmitted wave. Here's a little movie showing you what exactly is happening. So what we've got then is that we have the loudspeaker producing a sound wave which travels along to the right, and this reflects off the back end of the tube which is closed, and that reflected wave will travel along to the left. The result of this is you have got 2 waves travelling along that tube, one to the right and one to the left. The red wavelength there is the one which is transmitted, moving to the right, and the blue wave is the one which is reflected off the back of the wall, moving to the left. And as you can see, these waves are going to, in fact, cross over each other. They're going to interfere with each other. Therefore, when interference takes place, you either can have constructive interference or destructive interference, depending on which part of the wave you're adding to. Now, the resultant wave I'll show in black here, and you can see it there. And you can see what's happening to it. It's oscillating up and down. You can see like almost up and down as the 2 waves pass each other. You can see there's going to be points of maximum and also points of minimum. But if you look very closely, you can see there are going to be points where the resultant wave is not going to be moving at all. And these are called the nodes of the wave. Now, to see that a wee bit clearer, the resultant wave is going to become what we call a standing wave. And there's the resultant wave produced by the forward moving wave from the loudspeaker interfering with its reflection of the back wall, and you can see that's a typical standing wave. You're going to get parts of the wave where you're not going to get any movement at all, and that's the points which are marked on the diagram. Question 12a part 2. At 1 frequency the microphone detects a loud sound. The frequency produced by the signal generator is now increased gradually. Describe what happens to its loudness of the sound detected by the microphone as the frequency is being increased to twice its original value. Now, to answer this question, to give us a 2 marks, let's take a look at the simulation again where we have the forward moving transmitted wave and the reflected moving backwards wave, and see what happens to the resultant of those 2 waves when they're added together when we in fact change the frequency. Here's a snapshot of the 2 waves which are produced in the tube. The red wave represents the sound wave produced by the loudspeaker moving to the right, and the blue wave is its reflection of the back end of the tube. And the 2 waves are going to overlap, they're going to superimpose and give you a resultant wave which was shown in the diagram there. Now remember, just looking at a frozen moment in time, we're not actually watching the 2 waves move back and forward. Now we know that black wave represents the combined wave of the 2 waves in the tube, and it's actually in fact a standing wave. Now we're asked to increase the frequency of the supply and see what happens to the loudness of the sound produced, this standing wave produced. But the loudness we know is actually proportional to the square of the amplitude of a wave. So what we're going to do is replace that black wave with its amplitude squared and slightly factored down so we can fit it on the screen. And we'll represent that by a green wave. So we're going to take that wave away, the resultant wave away, and we're going to square its amplitude, and that will give us a value proportional to the sound. And that's represented by that green wave. So that green wave there represents the loudness of the sound. Now, to make the diagram a wee bit more clearer, I'm going to take away the 2 waves which are travelling in the tube. So we'll take those away and we'll see what we're left with. We're left with just a simple wave, and that's the wave, the resultant wave from the two travelling waves which have been superimposed, and that wave on the screen, that green wave, represents the loudness of the sound. Now the diagram is a lot more clearer and we can start to increase the frequency. So let's increase the frequency, and as we increase the frequency you can see that the loudness of the sound is becoming smaller, it's getting quieter. So as the frequency increases, it gets quieter until it gets to a point where it starts to increase again. So it's getting louder again. And now we've reached the signal generator frequency of double the frequency we had previously. And as you can see, the amplitude is now back up to its maximum. So we'll replay that again and show you what happened. There we go, originally, that's the original frequency. We start to increase the frequency, the loudness of the sound is going to decrease, and then it's going to increase back up to its maximum again when we get to double the frequency. Question 12 continued, part B. At specific frequencies the air in the tube will resonate. Frequencies that cause resonance can be determined by the relationship F equals NV divided by 4L, where we have V is the speed of sound in the air, L is the length of the tube, and N is the number of half wavelengths of sound waves in the tube. The student measures the length of the tube to be 2.00 plus or minus 0.02 metres, and the student also notes that the resonant frequency is 510 plus or minus 10 Hz when there are 11 half wavelengths of sound waves in the tube. So for 2 marks from part I, use the data obtained by the student to calculate a value for the speed of sound in the air. So let's start off with the relationship, and the relationship is that the frequency F is going to equal to NV divided by 4L. Now we've got to make sure that we're looking for the V part in this, so highlight that, and to do that we cross multiply, so it becomes 4L times the frequency is going to equal to NV. And remember, we're still after that V, so to have V on its own we must simply divide by N both sides, so we're going to have 4LF divided by N, and that's going to give us a value for V. So now we've got the value in relationship for V. What we do now is just plug in the numbers, so we can do this over here. We can say V is going to equal to 4 times the length of the tube, 2.00 metres, multiplied by the frequency, which is 510 Hz. Put a bracket around that to keep that tidy, and we're going to divide that by the number of half wavelengths, which is going to be 11, so it's going to be divided by 11. So we do that in our calculator, we end up with a value of 370.9, and of course units for the speed will be meters per second as that one. Now we can round that up to give us either 371 meters per second, or we can keep to two significant figures and write it as 370 meters per second. We want to keep it to two significant figures. Question 12, part B, part 2. Determine the absolute uncertainty in this value, and the value we're talking about is the speed of sound in that tube. And that was given by the expression V equals 4 times the length of the tube times the frequency of sound produced divided by N. And we were told that the two quantities in this expression, L was going to be equal to the length of the tube, which was a value of 2 meters plus or minus an absolute uncertainty of 0.02 of a meter. So that was the first measurements we made. The frequency, that was equal to 510 Hz plus or minus an absolute uncertainty of 10 Hz. And that's what we were given there. So here we have the absolute uncertainties here, and we've got the values here, so we can go to our data sheet, our relationship sheet, and look up how we combine uncertainties together when they're in a product. As you know, L and F are in the product here, and we can use the fractional uncertainties. We can change things round to give us the following. Instead of delta W over W, we can say delta V over V is equal to the square root of the first bracket will be in fact delta L over L, and remember to square that, plus the delta F, which is the absolute uncertainty in the frequency, divided by the frequency, and we have to square that, and remember we're taking the square root of everything from that. So delta V over V, we put in the numbers for this then. We're going to have the square root of, and the uncertainty in L over L will be 0.02 all divided by 2, and we have to square that, plus the uncertainty, the absolute uncertainty in the frequency, which was 10, so it's going to be 10 divided by the value, which is going to be 510, and we've got to square that as well. And remember, we're taking the square root of everything in that, those two squares. So we do that on our calculator, we get delta V over V, the absolute uncertainty in the speed, divided by the value of the speed, is going to give us a value of 0.2 if we do that in our calculator, 0.20. Just take your time, square these terms, add them together, and remember to take the square root of the whole expression. So I move the board up a wee bit. We can see that we've got delta V, the absolute uncertainty in the speed, divided by the speed. And we chose the speed, we worked out the speed to be the following. We worked out the value for the speed was equal to 370 meters per second. So the absolute uncertainty divided by the value of the speed is going to give you a value of 0.20. So we can cross multiply, and we can get the absolute uncertainty is 0.20 times 370, and if we do that, we get the following answer. We get an answer of 7.47, and we can round that up to give us a value of the following. We can say that delta V then is equal to, we just make it to one place once, then we can figure 8 meters per second. So therefore we have the absolute uncertainty will be plus or minus 8 meters per second. Question 12 continued, part C. The student now uses a graphical method to determine the speed of sound in air. Using a software graphing package, the student produces the graph shown in figure 12b. And there's the graph shown there, we can just fit it in the screen and no more. We can see that the y-axis is the frequency measured in hertz, ranging from the top value there of 900 all the way down to 0 there. And it's the x-axis which we're looking at here, which has got the strange x-axis variable of n over 4L. And that's measured in per meters. So how are we going to measure the speed of sound from this information? Because that's what the question is going to ask us. It's saying using information from the graph, determine the speed of sound in the air. So how are we going to do that one then? Well, obviously we have got to measure the gradient of that graph, but what's the gradient going to tell us? Well, let's go back to our original equation, which we were dealing with at the start of this question, and it was the speed of sound V is going to equal to 4, and it's going to be L, the length of the tube, times the frequency of sound created, divided by n number of half wavelengths which are in the tube, in the standing wave. Now, because we've got frequency on this side here, and we've also got frequency up here in the y-axis, maybe it's a good idea to have frequency the subject of this expression here, and that's what we're going to do then. So we cross multiply, and we get 4L times the frequency is going to equal to NV. We want to get F on its own, so we divide through by 4L, and we get frequency is going to equal to NV divided by, and it's going to be 4L, and that's exactly what we have in that bottom part of the graph. We have N over 4L. Now, we do know a very important thing about this work here is that it's a straight line, and straight lines are usually the form y equals a gradient times something to do with x. And our y is going to be the frequency, so we'll put down that, mapping it with y. And the frequency is going to equal to v, I'll write it this way, and I'll put this in a bracket, n over 4L. Now that's going to equal to this part here, v will be really the gradient m, and n over 4L, as you can remember, n over 4L is in fact the x variable. So n over 4L is the x variable, so therefore we can write down x for that. So there's our equation for a straight line, and because we're using this frequency for the y-axis, and we're using n over 4L for the x-axis, then it would seem from that if we work out the gradient, we can find the speed of sound in the air. So that's how we're going to do it. Work out the gradient of the graph, and it's just going to give us the value for the speed of sound in the air. So now let's work out the gradient of the graph, and to do that we have to select 2 points on the graph which are quite far apart on the line, and we must make sure we know the scales of the graph as well so we can calculate the correct coordinates. So going along the way the x-axis, we can see that we have a range of 10 boxes to represent 0.15 of the x coordinate along the way. We'll just call it the x coordinate. So that must mean that one little box must represent 0.05, and we can put that down like that. One box going along the way is going to be equal to 0.05. So just remember that one. And get up the way is the same idea. The y-axis, we've got a range from 0 to 100 Hertz covering 10 boxes. And that must mean that one box stands for 10 Hertz. So we can put that down as well, that one box stands for 10 Hertz. So now we've got our scale. We now go and select 2 points which are quite far away from each other. And the 2 points I've selected are the 2 points here which are on the screen. This one here and this one up here. And I've chosen those 2 points because they cross exactly, the line crosses exactly where two of the lines in the graph cross. So it makes it easy for identifying the coordinates. So the first one is this one here. We can now name it, and that's this point here, and it's got coordinates 0.45 and 190 because it's 9 boxes along. So 9 times 0.05 is going to give us 0.45, and it's going to be 19 boxes up, and 19 times 10 is going to give us 190. So we've got our first coordinate there. Our second coordinate is done by the same method, and that's going to give us a second coordinate up here crossing the box to be 2 and 710. So we've got our 2 coordinates now. Now all we need to do is find the gradient of the line between these 2 points. And we know fine well that the gradient in terms of our maths class, the gradient m, is going to equal to the difference in the y coordinates, y2 minus y1. We'll put a bracket around that, and divided by the difference in the x coordinates, x2 minus x1, as long as we keep the same order. So let's work this out then. We'll call these the y2 and x2 coordinates, and these the x1 and the y1 coordinates. So we have the following: gradient m is going to equal to, and y2 is going to give you 710. Take away y1, and y1 is going to give you 190. So we have our top value, and we divide that by the difference in the x coordinates. So x2 is going to be 2, put a bracket around here, and we're taking away x1, which is 0.45. So there we have our calculation for our gradient, and if we do that on our calculators, we end up with a value of the gradient to be 335, and therefore that must mean that the speed of sound, which is the gradient of the graph, is going to be equal to 335 meters per second. So we've now found the speed of sound in air in the tube to be 335 meters per second from the graph. Question 12, C part 2. Using the graphing package, the student estimates a 2% uncertainty in the value of the speed of sound in the air obtained. And part A says, state how the precision of the value obtained by the graphical method compares with the precision of the value obtained in part B. So let's take a look at that part first. Here is a summary of our results which we had in the question. We can see by the graphical method we had the speed of sound in air to be 335 meters per second plus or minus a percentage uncertainty of 2%. And for the practical method we had 370 plus or minus 8 meters per second. Now our definition of something that's precise is as follows. Measurements are precise when they give the same or similar results. So we're looking for the percentage error for the practical method to be around about 2%, so that we can say whether these two results are both precise. So let's calculate the percentage error for the practical method. Remember, the percentage error for the practical method we can write as follows. We can say percentage error, or a percentage uncertainty, is going to equal to the uncertainty in the speeds, which we'll say is delta V, divided by the actual value V, and we multiply that by 100% to get our answer. So the percentage uncertainty, we'll call it percentage U, is equal to 8 divided by 370, and we change it into a percentage by multiplying by 100. And if we do that in our calculator, we get the percentage uncertainty is going to equal to 2.1%, which we'll reduce to about 2%. So you can see that both are given 2%. So the practical method has got an uncertainty of 2%, which means that they give similar results. So in the first method, the graphical method, you've got plus or minus 2% absolute percentage error, 2% spread in the possible answers from the mean. And for the practical method, you get a 2% spread as well. So what we can say for that one is that the precision values obtained in both the experiments we carried out, the graphical and the practical method, is the same. Now the part B one says state how the accuracy of the value obtained by the graphical method compares with the accuracy of the value obtained in part B. Now our definition for accuracy is as follows. Our definition of accuracy is that measurements are accurate when they are close to the actual value. Now the value for the speed of sound in air, we're going to take a value equal to 340 meters per second. That's the value we're going to take for the speed of sound in air. Now you can see for the graphical method, we're going to have 335 plus or minus 2%, and that's going to give us quite accurate value, quite accurate measurement to the true value. So that's actually quite a good answer there. 335, that's an accurate version. 370 plus or minus 8 is not going to give you as accurate a value as our stated value. So in this case, it is the graphical method which is going to give us the most accurate answer. The last part of question 12, part 3, it says the line of best fit on the graph does not pass through the origin as theory predicts. This may be due to a systematic uncertainty. And we have to suggest for just 1 mark a possible source of systematic uncertainty in the experiment. Systematic uncertainties are very difficult to find in experiments. You have to check everything out. But maybe there's a clue from the graph. You can see that the graph does not pass through the origin, but in order to make it pass through the origin, I have to decrease it in the y direction, which must mean that my original y direction y-axis measurements may be too high. So that must mean we're measuring the frequency too high. And also to get it down towards the origin, I have to decrease the x value as well, which must mean whatever I'm measuring the x value is too high as well. And that's the case of the L, the length of the tube. So we can summarise up the following. We can say that there is a systematic error in that experiment, a systematic uncertainty. And there's 2 possibilities. And the first possibility is that we're measuring the frequency too high. So this could be a fault of the actual signal generator. Maybe the dial has been moved by too much usage, and we're recording a value for the frequency which is much higher than what it is. Maybe a good way to solve that systematic uncertainty is to use an oscilloscope and see what the true value of the frequency output is from the signal generator. Another possibility, well, we can guess that it might be due to the length of the tube being too high. Now, you'd have to really muck that up not to be able to get the exact length of the tube, but maybe it's a pre-made tube size and it's got a label on it and the label has come off and it's maybe giving the wrong value. These are things you have to take into account in every experiment. Check, check and check. So there's a systematic uncertainty, 2 possible ones. Either the frequency measurement is too high or the length of the tube could be high.